Okay, thanks, Albert. Hopefully everyone can hear me. We'll be looking at the chat. We'll be answering questions. Again, I'll introduce myself again. I'm Juan Rosales. I'm a solution engineer for the electronics products here at Altair. Been working on power conversion about 2 years with Albert and all that. So a novice in theory, but I've been learning a lot. And today we're going to talk about thermals. So coupling thermal FEA analysis with thermal electrical analysis or simulation. And for that, I have this agenda. So first, introductions or housekeeping, which is what we just did. And then we have my second topic, which is the MyWay case. So one important thing that always is commented is how do we validate the simulations we perform, the solutions we sell. The MyWay case was something that we did last year where we were able to validate these workflows. And then we'll look at a brief overview of what this workflow is, what its contents are. And then we're going to look at how from this workflow we can extract fit models and we can include them onto system level simulations. And we'll talk about more in depth on what is a fit model. And then the actual meat and gritty of this presentation is the demonstration. So what I'm going to do is run you through the whole process, through the whole workflow that is coupling these two solutions, and then having results at the output, making a fit model, everything, almost everything, at least solving in real time. And so let's skip over my next few slides, which were housekeeping. Okay, so the MyWay case. So somewhere around last year, maybe around this time, we collaborated with MyWay in Japan, which has been a long-term channel partner of ours. So they had an inverter. So they had a product, and they had their thermals. So they measured the thermals with thermal camera and sensors. And our task was to do essentially a digital twin. So model everything we had. They shared with us the CAD files, and then we modeled the inverter with PSIM, and then we made a simulation. And then the idea was to correlate to actual test measurements. So there are mainly two challenges, right? So first, to calculate an accurate depiction of the losses of from the electrical part. So something that depends on temperature of the operating point of the transistors or of the switching devices. And the other challenge was how complex was this ensemble? As you can see, it is not just the main inverter and a heatsink. It actually has 5 fans on the inside. It has an external case, which is relatively complex ensemble. Has a heatsink, which is not, a super simple geometry. And the idea was to model the whole thing or to simulate the whole thing and how the whole thing will behave. Now, before going further onto the results and the work we did, I would like to talk a bit about the tool so that you have prior context of the characters of this story. So first is SimLab. SimLab is our multi-physics platform. And it is not just one program that does everything. In theory, it's a set of small programs or small solvers for different applications. And everything is under the same preprocessor, which is very friendly for us. Now, the cool thing about SimLab is that its electronics thermal solver is more tailored to our needs as electronics engineers. And it doesn't require for us to have a lot of experience on CFD or even in FEA. So meshing, modeling is pretty straightforward with these tools. And we'll get to experience that in some minutes. And of course, it has other applications. This could be something ranging from structural, so stress, vibration, to flow simulations, which are not the ones that we're covering today. And also now including low frequency and high frequency electromagnetics between whole other range of applications. And then we have PSIM, which is the one that lies at the center of everything, and the one where, well, both Albert and myself belong to. And PSIM is a purpose-specific power electronic simulation software. It is intended, or its design is intended to deal with the fast and accurate transitions of a switching converter. And it's by doing that, it is very fast and very accurate. Other features we include the capability of doing control design with the frequency response of the converter. We can do thermal simulations, which is the main topic for today, obtaining both conduction and switching losses, again, in a very fast and accurate manner. And also added to this, motor-derived simulations as we have seen in the past webinar, and conducted EMI simulations also. And then the third main character of this story is HyperStudy. HyperStudy is our design of experiments, optimization, and fit model generation tool. And the idea is it's kind of like this master of puppets tool, where it doesn't matter which platform we're using, which solver or simulation software we're using, we should be able to design experiments, set them up, and run them. And it's also capable of leveraging multiple CPU cores, so running a number of simulations at the same time. And the other applications besides optimization and fit models is to perform sensitivity analysis. So those are the main characters. So just quickly going over this. These were the results. So MyWay had their own results, which they capture here, as you can see in this table. And then we had ours, which are here, which you can see here in the complete simulation on the left. And we can see that we had a very good correlation between the experimental and the simulation data. And you can look at that the thermals is one thing, but the airflow is another complex thing that's happening inside the box. You can see that the path of the airflow is very complicated, and the ensemble also makes it very complicated. But again, this is not super hard to set up, and we don't need to be very skilled. We don't have to need prior FEA skills to maybe get around this. Now, I would like to talk a bit about thermal modeling. So how do we model behavior with both tools? On one end, with PSIM, we have our thermal models, which are for our switching devices. So these models are ideal. They have an ideal on-off transitions, and so they are pretty fast solving. And the voltage drop across these devices is updated so that we can keep calculating accurate losses. And these losses, both switching and conduction, are obtained or are calculated from lookup tables. An array of lookup tables, as we'll see in a couple of minutes, and they are properly scaled and do take account a lot of conditions within the circuit. And last but not least, how we model the interface between the junction and the case is by using either a Sauer or a Foster network. And outside of the device, we can place another thermal network, which could be representative of our cooling solution, maybe if it's passive as a heatsink or something like that. And now on the SimLab side, we have, it's fairly simple. So for the electronics components that dissipate power, we just need a 2R component, which we can quickly obtain from what's inside PSIM. And regarding cooling solutions, the only thing we really need to care about is how we model the fans. The most effective way of modeling fans is by using the PQ curves, which we can find on data sheets. Other than that, we just really care about assigning the right materials to the right bodies and making sure that everything is that everything makes sense on that end, right? Now, let's talk a bit about the workflow. So the workflow is an iterative workflow at the moment, but some features between PSIM and SimLab allow for easier coupling between both. So what we should do first is we start with a PSIM simulation. This PSIM simulation has a fixed case temperature, which is going to be kind of our initial condition for the whole thing. Then from that PSIM simulation, we have losses and a model for SimLab to process. Now on SimLab, we should have our complete model. We should have the materials assigned, and maybe some simplifications about certain geometries that might be troubling. But other than that, we just need our model to be as it comes. We can assign those losses and those models to the bodies inside SimLab, perform a thermal simulation, or thermal and flow simulation, and then we just need to keep exchanging results between these two. Because, of course, if, for instance, the heating of, well, given a power loss, we'll get to a case temperature inside SimLab, right? And that case temperature is, of course, different than the initial condition we had at the beginning. And whenever we change this initial temperature with the one we got from SimLab, we're going to get a different operating point for the transistors. And this will happen, and we'll keep doing these types of simulations till we converge to a certain value. There are some details within these tools that makes these simulations go faster, and we'll look at those in a second so that you don't think that this is going to be very slow or inefficient. But yeah, so that was kind of like the overview I wanted to give. So I want most of the information to come from the demo. So let's actually do that. So let me escape here. And let me show you the simulation models we're working with. So here I have SimLab. And within SimLab, I have this PCB, which was designed on Altium Designer. And let me show everything in a prettier color. Everything here was designed in Altium Designer except for the fan, which is this structure here, and then the heatsink here. So other than that, everything comes from Altium Designer, and SimLab is able to import Altium Designer files or ODB++ files if you want something vendor neutral. But yeah, okay. So let's look at the PSIM model before continuing with these details here. So let me pull up these. So this is a PSIM schematic, and this is where we start with the workflow and where we start looking at the requirements from the simulations, or yeah, the requirements for the simulations. First, let's explain what's happening here. So here we have a three-phase inverter, pretty straightforward. We have an RL load. Here at the right, I have designed some PI controllers for this inverter. As we can see here, we're controlling in the DQ frame, and then giving the references to the inverter, and then generating the PWM waveforms. So on that end, pretty straightforward. Now, a requirement for this workflow to work is we need a certain degree of parameterization, specifically for the case temperatures of the devices. Now let's see exactly what are we looking at here in terms of the devices. So here's a MOSFET. If I open it, the model level or the type of model we're dealing with is a thermal one, and I've selected this wolf speed part. And just for you guys to see what's inside this model, we click here, go to device, and we can see that for each of one of these devices in this list, we have an array of curves and or equations to define how we calculate losses. All of these we find either on the data sheet, or we request the manufacturer to either create a model or to send us the adequate information. But we can see that this is practically the information that we need, right? So we have BDS versus IDS so that we can get conduction losses. Then from there, we can go towards turn on energy and turn off energy, from which we can calculate losses. And then we can also take into account the gate resistors from the gate drive from the gate drive circuit, and we can calibrate our losses according to this. Now, all of these curves, or most of them, are temperature dependent. So the temperature of the junction will change how we get losses, which is, the main, the core of this workflow, right? The changing in operation, the change of operation with temperature. The same thing goes with the diode. And here on the lower side of the window is where we can see the models, how we are modeling this interface between the junction and the case of the device. Okay. So with that being said, where we're looking at here, this little node to the right of the component is the case of the device. And to this case of the device, I'm just placing a constant. So we are fixing that temperature. We're not placing a thermal equivalent circuit as we have seen in the slides. I'm fixing this temperature because this is what the workflow requires. And you can see that the value of this temperature has been parameterized. This is one of the requirements we need for coupling both solutions, and I'll get onto more details in a second. So each one of these MOSFETs is being parameterized and its case temperature is being fixed. Now, for initial values and all of these parameters or all of the definitions of these variables are in these in this parameter file or in this text file. So pretty straightforward. We're working for the variables, we're working on Kelvin, and PSIM overall works with Celsius, with degrees Celsius. Inside these constant, I perform the operation from Kelvin to Celsius. So yeah, that deals with units. So let's quickly simulate this and see exactly what happens, or how do we start this workflow. Let me save this and let's start simulating. So another detail is this simulation includes dead time on its PWM generation. So it's maybe a bit slower than other simulations that wouldn't include that time, but it's still very fast. And we're actually just a couple of seconds more. And there it is. Okay, so we can see our three phases going, they look good. They look as expected. And if we go to the directory of this, where this simulation is, which is right here, PSIM has generated this CSV file. Now let's see what the contents of this CSV file are. We can see that it has generated a table where we have each transistor. We have a dissipated power. And then we have a 2 resistor model. So we have junction to case, case to board, or backwards, junction to case and junction to board. And then we have some safe temperature margins here. And we also have the part number, which is we're not going to use. Okay, so this file can be read by SimLab, and SimLab, by reading this CSV file, will automatically assign the 2R models and the losses to the bodies in the simulation. So that deals with the PSIM part. Let's look at in my opinion, the fun part in this scenario. So here we have a fairly detailed model. As we can see, all transistors have their legs in, and we even have the logos of each manufacturer in some of them. So this is pretty detailed. Now, specifically when we are assigning losses or assigning models to these switches, we might come into some issues if we don't, if the mesh is not, small enough. So I'm gonna simplify this. Simplifying your thermal loads onto boxes is really helpful in these cases, and this is the same thing we did for the MyWay case. So originally in the MyWay model, there were these very complete models of the switching devices, but we simplified them to boxes so that it was easier. So we can quickly do this within SimLab, and let me explain quickly the interface, which is pretty straightforward. We have a top ribbon where we can just explore different categories and different actions and different items. And on the left here, on a bit down, we have our assembly browser where we can look at all of the elements of our model. And we can also look at the setup of our simulation. So first step, simplify. So I just want to simplify these transistors here. And we can do this by using this element, which is specific for the electronics workflows. And we can choose the shape for these models to simplify. We can just select one. And here on the lower side, we have a option that tells us to simplify bodies identical to the input ones. We can do that without any issues. And we can delete also the input ones because we don't want that overlap between both. So let's click OK. Magically, everything is correct. I might need to change the names here, but we can see that simplification was pretty straightforward. Now, the names of the bodies are pretty important because this is how we relate that CSV file with the with each body and how we are able to assign these models to them. So let me quickly change these names. Let's do 3, 4, Q5, and Q6. Okay, perfect. So everything should be done. We just need to assign a couple of materials and then we're good. But first, I would like to create what we call a solution. So we go to these solution tabs. Here's where the multiphysics aspect is more represented. Here you can choose between a very wild array of solutions or of simulation types: structural, thermal flow, particle simulations, electromagnetics. But we're going to focus today on the electronics part, and specifically on electronics thermal. The thing we need to do is to practically just select all of the bodies we want to take into account in the simulation. Today we're doing steady state. We can also do transient, and but of course it's much faster to do steady state. And we need to choose what's the simulation type. So instead of just, we can choose how the degree of, let's say, fidelity we can perform in simulation. We can do just thermal with normal convection over everything. We can do thermal flow, which is what we're doing because we are forcing flow with the fan. We can do thermal and frozen flow or just flow simulations. So thermal and flow is okay. Then flow regime. We have the options for turbulent and laminar. Turbulent is the option here for a fan. The turbulence model, we can choose it. To be honest, I have no idea what the options here are, but the default is okay. We, just as an FYI, we can include electrical effects in these types of simulations. We cannot include effects like skin, like the skin effect. We can only focus on DC currents flowing through these traces and looking at the heat distribution. This is not the case. We're not going to include them today, but we are including gravity. So let's go ahead. Yeah. And there it is. So we have created a solution, which is this here in the solution browser. And now we just need to set up. And the first thing we would like to do is thinking about meshing. Meshing can be a troubling topic. With SimLab, or at least specifically for SimLab or for electronics thermal applications, it is fairly straightforward. The only thing we need to ask SimLab, or we need to be mindful of, is for SimLab to keep the laminated structure of the PCB if we so desire to keep it. SimLab has a lot of options to simplify a PCB to maybe more efficient components. We can average out the PCB to one material. We can do what we called a mapping of the copper distribution inside a PCB. But in this case, I'm doing the most simple approach, which is just mesh it as it is. And to help us keep these laminated structures, the creators of eFlow have created key planes. Now, what are key planes? Key planes are planes that allows us to keep certain geometries. Let's see exactly what they are. So I've just placed key planes everywhere that's parallel to the board within the board objects. So as we can see, these key planes are these transparent planes between each layer. And these transparent planes within each layer will force the meshing process to keep these structures without us needing to have a very small mesh size for the whole thing. So the solver will allow to have, for instance, a relatively big mesh in XY coordinates and in Z coordinates, except for the things that are constrained within the key planes. And we'll see this once we start meshing the whole thing. But anyways, this is the only consideration, or one of the two considerations we need to have when we are meshing these types of models. Let me bring back the color so that we can see it. Then we need to think about discretization. So it is fairly straightforward. What we do with electronic simulations, or what we do with the mesh of electronics thermal simulations, is to do a Cartesian mesh, which is a hex mesh, but that's referenced to the Cartesian axis of the whole model. So in other words, it's just a voxel type of mesh, right? So we can just place the resolution of these voxels, and in this case, I'm going to put 0.5 millimeters for X, the same for Y. Then for C, I'm keeping it as 1. And now this last field is telling us how small is the distance, how small can the distance between key planes be? And since the distance is fairly small in this case, I'm going to give it something relatively small. We're going to disable this because we don't need to create the mesh right now. Before simulating or before starting the simulation, SimLab always creates another mesh. So let's click OK. And let's keep going on to the models. So if we model these sorts of components with something we call smart objects. And smart objects allows us to quickly model different things in an electronics ensemble, like 2 resistor components, which we're going to use for our transistors, fans, vents, sensors, liquid cooling, thermoelectric cooling, so Peltier cells, and other devices. So with the CSV file I've created with PSIM, I can create a 2-hour component object. So I just need to select the board bodies, which are here. I need to import the file generated by PSIM and click OK. Let's just wait for everything to be assigned. And just wait for it. While that happens, the following steps would be to define the fan. as I mentioned previously, the fan we can define with the PQ curve, and for that I have this CSV file, which has this curve defined, and SimLab is able to import that within the fan, within the fan smart object. So let's wait a bit for this to finish, and so yeah, then what else can we do? Okay, so let's explain. I don't want us to get hung up waiting a lot for this. So let's go back to some slides I had here. Okay, while we wait. Let's talk about fit models for a second and let's introduce them while this happens. So a fit model is, let me get to presentation mode. Change this. So a fit model is a mathematical model that's a representation of a higher fidelity or a more complex system. And we train this model with simulation data, or actually with any type of data you have. If you have, for instance, a CSV file that has a lot of inputs and outputs, we can create a fit model with those. We just need, at the end, we just need data. Now, these are very lightweight, and this is what we use for system level simulations, for us to introduce a bit more complexity onto system level simulations. And how we generate these models is pretty straightforward. We have a physics model. So in this case, we have either PSIM or we have SimLab with the thermal part. And then we start doing a lot of simulations, between 10 and 100, something like that. And then HyperStudy will be in charge of leveraging those simulation models and those simulations to train a model, a mathematical model, and with that, we can get a system simulation. Now, for this session, what I want to do is a fit model of the system we're working right now in SimLab. So getting the losses from the device as an input parameter, then create a fit model of the PCB, the heatsink, and the fan, and all together into one simple box. And then at the output, get each device's individual temperature. Okay, so let's see if SimLab is back. I believe it's a bit hung, so let's move to another model I have here. So let's just have this here, and I want to be cognizant of time also. So let me just grab another file here, and let me show you the next steps. Study. Okay, let's just a second for me to open this soft. Okay, perfect. Okay. Yeah, it seems we say normally that in a demo the softwares can smell fear. So it practically, I believe, SimLab just noticed I was a bit nervous about today, I guess.
And no worries, Juan. We can also blame WebEx for potentially sucking up too much resources.
Leveraging, our graphics drivers usually scream with this type of load, right? Yeah. Having 3D things, sharing screen, it's awful. But yeah, okay. So what should have happened after SimLab got hung up is it should have created these smart objects. So each smart object has a power distribution defined, has a resistance for junction to case, and has a resistance for junction to board. And how do we define this? And let me quickly delete one and create one so that you can see how this was done. So going to solutions, it current? Yeah. So click on Smart Objects, select to resistor. We just need to select the body, select the total dissipation. Then we select the phases, what's junction to case, what is junction to board, then define some resistances in there. For instance, something that makes sense for this, 10. Since we're doing bottom side cooled, that we expect the resistance from the junction to the bottom or to the board to be less, right? So 0.22 should be fine. For this, we were dissipating around 18 watts for this. Okay. Yeah, okay. So yeah, this was already defined, but this is how everything should look. Now, regarding the fan, details about the fan modeling. So I had this fan structure. I did not have a model of the blades or a model of the shaft or the motor. And the reality is that we don't need it. We just need a volumetric body that represents the blades. And if we go on to the definition, we just need to click on it, click fan. We need to select that body that's representative of the blades. And then we just need to select the PQ curve, which we can just import from the CSV file I just mentioned previously. And then, yeah, we can start adding some heat generation to the hub of the fan or stuff like that. But other than that, it's pretty straightforward. We don't need to deal with other stuff like this. Another detail is we also need to define the computational domain, which is to define the boundaries of the volume that we are going to be analyzing. And to define this is fairly straightforward. And let me delete this. We just need to go onto computational domain, select our whole body, and then do some adjustments as desired. For instance, I would like, since airflow is flowing from this, from the inlet here in this fan towards the heatsink, I might want a bit more space before the heatsink and after, before the fan and after the heatsink, and maybe make this smaller so that we don't have a bunch of elements flying around there. Okay, so this is practically the setup, and I would like to simulate it. So let's simulate it and let's see how long it takes. I do have a finished product if it doesn't end up. But I would also like for you guys to look at the finished product here. Okay, so let's. It seems that there were no materials to this.
So, Juan, while this is running, there was a question in the chat about importing PCB schematics and stuff like that. I don't know if you need to do a demo of that, but that's relatively straightforward to do, is to import an Altium PCB model into this environment, correct?
Yeah, correct. So as we can see here, and let's skip the solving part, but as we can see here, if we go onto import and then CAD, some of the file formats that we're going to find is Altium, or we have this ECAD section. And this ECAD section, we can import an AutoB++ or an Altium Designer or an IPC 2581, Siemens, Suken, Expeditions, Allegro. All of those files are here. And if those file formats include the 3D models of the components, this will be included also inside the simulation. But anyway, while this starts solving, and if it ends in time, I'll just show you the finished product that I have here. So this is the finished product on the right. As we can see, we have a very nice temperature map of the temperatures of the whole thing. And if we look at the cross section of this, and let's look at cross section in the x-axis, we can see how each component is dissipating heat towards the heatsink through the board adequately, and how it's also heating the air around it. And we can also look at, and let's change the axis here to the seam. Let's also look at velocity, air velocity. So we can look at kind of like the dynamics of the fan, of the air flowing through the system. we can see air flowing from the fan towards the heatsink and cooling it off. And so yeah. So as I mentioned previously, the idea from this workflow would be for us to export these losses onto PSIM again, and then keep doing that exchange till we reach a certain point of convergence. Now, SimLab also exports one file for PSIM to interpret. And if we go to results and then the results folder, we can see that a parameter file, let's look for it. Is this? Should be around here. We can see that a parameter file was generated. So this parameter file should have the case temperatures of all devices. And this parameter file is the same one that we need to either copy the parameters or to import from PSIM that parameter file into here. Okay. So now, and the workflow should continue. Now, to make things easier for whenever we restart a simulation, we have this function. If we right click here to solve, we have this function that's called restart and update. And this function allows us to get a results file, this .rst file, and relaunch the simulation from by including the past the past data, so that we don't have to a lot of time on simulating in the next iterations. So this is a very nice feature, and let's actually try it out. So from here, yes, and we'll see how it starts simulating. And while that happens, I would like to show you how would I create a fit model of this system. I'm sorry if I'm jumping around with all of these things, but I do want to be cognizant of time. And for that, let's head out to this simulation, which is the same. Again, we're working with all the same simulations. So SimLab has a very easy way of creating a hyper-study design of experiments. And with that, we can create a fit model. So if we go to solutions, we have this DOE option, and we have the option to create a DOE with using a solution. And this DOE we need just to select this solution, which was the one I have previously set up. Click OK. And we just need to define parameters. So we need for some part of this design to be parameterized. This is not only for power values, this could be also for the resistance values. This could be also for a parametric design. So if we have some parametric design, or if we have the design of the heatsink to be parameterized, if we want to do some optimization, whatever, we just need parameters here. Click OK. And now with parameters defined, we just need to tell, we can automatically create the hyper-study file with this. And we'll go on to the hyper-study project in a second while this opens. So everything is done in the background. It's just one click. And then we just need to follow a very simple set of steps to create this fit model. Now, okay, there it is. Seems almost done. Hyper-study is opening. We have a lot of activity in the chat. Hopefully we'll get to that later. Okay, so this is how a hyper-study looks.
Juan, don't worry about the chat. I'm answering the questions.
Okay, perfect. Thank you. So yeah, looking at the definition. So this is hyper-study. This is the general tool that will allow us to do design of experiments. It is able to be compatible with any simulation tool you might have. In this case, it automatically created a project for us, and this project is already set up. And we just need to practically click next in this lower part of the menus. So first, include import variables. Click yes. This will import the parameters that we have previously defined in SimLab. So I have in SimLab parameterized the dissipated power of each one of these devices. And here we have those parameters, and we can define a lower bound and an upper bound for those. Now, the next steps are pretty straightforward. HyperStudy is going to do a trial run or a test run where we can extract the outputs that we are going to post-process. Now, as any good cooking show, I already have a finished product in here. And we can see that the models were properly tested. This is our first initial test run. And then here are our outputs, the temperature of each device and the value of the first iteration or of this first simulation. The next step was for us to create a DOE. Now, within the space defined by the bounds of these variables, we have defined a DOE. We have defined 31 runs. This is just the method by which we choose each point in this in the simulation space or in this space defined by the input variables. And then we have evaluated all simulations. Each SimLab simulation uses can use as much cores as we want. I set SimLab to use 6 cores for this, so I'm able to simulate 2 simultaneous simulations without sacrificing my computer. So all simulations were done, all data was extracted. This table is just which value was selected for each power and what were the outputs for each transistor, what was the output temperature for each transistor. Then we don't care about post-processing, but what we did is to create a fit, and we can create a fit model for existing data. It is super quick. It just 2 clicks to create a fit data. And what I want to show you is the actual fit model working, which is right here. So these are the inputs, and I'm able to switch to select any input power for all of the 6 devices. And then here on the lower side, we can see the output, right? So the output temperature in Kelvin. So we can see very intuitively, if I make P1 or the power of Q1 going up, the temperature is going up. If I do P2 down, it's also bringing the temperature of Q2 down, but it's also impacting the neighboring components, right? So it's just not the relationship between this transistor's dissipation or loss and its temperature. Is also the relationship between them, the fan in action, the heatsink in action, the PCB also dissipating a bit of power or sharing a bit of heat between these devices. So this model can be nicely exported onto a block, which we can use onto a system level simulation. And it is practically the same thing. So let's see how my simulation is going. If I should have it somewhere in there. But okay, here it is. Oh, this was the last one. But yeah, I want to be cognizant of time. Yeah, I don't want to take a lot of time from you guys, since we are getting close to the end of this session. So with that, let's just look at the results. With that, I hope you have a good idea of how we couple these these 2 tools. If you wonder about how long this would take if I did it live, if I go and view this and look at the solver log, we can see that each iteration took about 0.6 seconds. So this iteration, 0.6 seconds, this other one, 0.6, 0.15. So, and this is the one that I just started by using the results file, right? So the previous one might have taken a bit longer, but this one took far, far less. So that's, yeah, a great way of restarting a simulation by using what we already done. Okay, so I want to give a space for, having these questions in the chat. So I would like to conclude that yes, this workflow is fairly manual, but we're working on being more automatic. What I mean is, after each iteration, SimLab should be able to call PSIM. PSIM is fairly fast, lightweight, and these simulations don't take a lot of time. It takes this schematic to run about the same time of one iteration of SimLab or of this thermal simulation. So coupling both automatically shouldn't be any issue and shouldn't be a compromise in simulation time. So in us doing doing more work, right? So it is really nice in that sense. So yeah, with that, thank you for listening. If you have questions, we'll keep answering them. Let's see.
So there's been a bunch of questions. Thank you so much, Juan. So I think kind of getting to things, there was a question about the fit models.
Yeah.
So that fit model you were showing, if you want to go back to it, Juan, this is just the parameter set. Can you go to the export options? If you go to the report, so you can export this as an FMU or as the hyperstudy fit model, and then that model you just couple to your system simulation. So then what we would do there is you'd couple PSIM with the fit model instead of needing to couple it with the CFD tool. That's the workflow we're proposing here, right, Juan?
Yeah, correct. So it is that, yeah, we can export this as a block, and maybe I can show it if Activate likes to open. But yeah.
Okay.
Let's see, we have another question about interfacing the heatsink with the board.
Yeah.
So at the moment, the heatsink is directly with the board, just for simplicity's sake. But there are two ways we can include a thermal interface material. One is by literally including the geometry, so a laminate body between the heatsink and the board, and then assigning the correct material to it. And another one is we have this, let's go to the solution here. And the other one is we have this resistance element. This resistance element, we just need to select two faces, and then we define a thermal resistance between them, and that could be our thermal interface material or medium. So hopefully that answers your question. Hitting more realistic. Yeah.
So did you see the one about how much data it takes to create the fit model?
Yeah. So data, we can take as much as we can use as much as we'd like, really. But if I go to mine, in this case, I did 31 simulations, and HyperStudy was able to simulate 2 at a time. This didn't take a lot. Again, in each one of these simulations, we are using the previous one as an initial condition to get the next one. And
I think Juan, I think that's a good point to make. Is with SimLab, you don't need to solve the transient all the time. Like you can solve just from an initial condition, and it's quite a bit faster to solve the second or third time with SimLab. You don't. I think if you do I've seen situations where you've had like a super complicated CFD model that takes like maybe 24 hours to solve, and then when you do the initial conditions, it's solved in like a half hour or so. Not saying that this model takes that long to solve, but that's the kind of speed up you can see when you use the initial condition setup. If you can go back to HyperStudy, Juan, there's the quality factor as well. So HyperStudy automatically allows you to see the quality of the fit model and the predictions. And you can see quality can be there. And as you move around, like you can see how, so maybe Juan's model, I don't know if I can see those numbers properly, but some of you can see where it's good and where it isn't. And then there is some diagnostics you can do to ensure that you've got a good enough model. And if you need to have more data at certain points, you can bring that stuff in. So yeah, HyperStudy is pretty user friendly for making sure you have quality.
Correct. And also regarding the time to create the fit. So to train this model, it really takes a couple of seconds. The heavy part of the workflow is to actually do the design of experiments or the whole bunch of simulations, which also for this specific model, which is pretty lightweight, it doesn't take a lot. But the fit should be done in seconds.
Yeah. Yeah. Okay, and there were some questions earlier. I'm not sure. So just kind of cognizant, we've got like about a couple minutes left here. There was a couple of questions a lot earlier about underlying models. So the PSIM thermal models are an ideal switch that use big lookup tables for the switching loss calculation and the conduction loss calculation. This allows us to abstract away a certain level of detail and have fast simulations. So we're trading a little bit of fidelity there for simulation speed. If we were to have a super detailed switch transition, it would cause us to have super slow simulations. But yeah, so we do get very good loss calculations. If you want to get into like the dV by dt, di by dt interactions, you should look at using the level 2 models, which is sort of a different topic. But yeah, we can still properly model things like soft switching can still be properly modeled because that we just basically put an external capacitor onto the model, and that allows us to look at the resonance there in the soft switching. Juan, can you pull up the summary slide again? Sorry, the upcoming information in the PowerPoint.
Let's see where I got
So just as a kind of comment, next week I'll turn my camera back on. Next week we're at APEC, so swing by the booth if you're going to be there. We're going to be towards the back near the food and beverage. I have a session on Tuesday. Juan will be at the booth as well, so you can pepper him with questions if you didn't get a chance. And then look for the upcoming sessions. Look for the upcoming sessions that are coming for this webinar series. Again, second Thursday of the month, we're running this, and I hope that kind of covers everything. So there's so this recording will get posted to YouTube. There's a question about the regression model that was used in this case. I'll have to ask one of the HyperStudy experts there's a number of different models that are available for regression modeling. So the video will be up, we'll post that out, and we've hit the top of the hour. Thank you so much for your time, guys. Juan, thank you, excellent job.
Thanks, everyone.
If you have any other questions, just drop us a line. Bye, guys.